So there is we have discussed for the vertical surfaces, for the horizontal and vertical plane surfaces we have discussed, and we have also discussed for the inclined surface what is the total force. Now there is another method for these plane surfaces, and that is the pressure diagram method, that is force calculation based on pressure diagram for your plane surfaces. When horizontal is not at all needed, so vertical, and for your inclined you can just adopt this also, this procedure also. So let's take vertical surfaces, and let's say the height is h1 for the top, and for the bottom the height is h2. Okay, so now the pressure here is rho g h1, and the pressure here will increase, and it is rho g h2. So your distribution of the pressure is something like this, linear with the linear increase with the height. This is how it varies. Okay, so if I happen to draw a pressure diagram, so this is in this view, so let me draw a pressure diagram with the area, so if this is rectangle, I mean if I assume that it's a plain rectangle surface, so it will be something like this. So these are for rectangle. I mean this pressure diagram will help easily, you can help, I mean useful for if it is a rectangular cross section, and you can the same logic will exist for other things, but we are building for rectangular. So this height is basically into this. So if I just see the side view, this is how it looks, side view of this area. So now the pressure everywhere on this will be same, because pressure varies with only height, it will not vary with the, so this is rho g, and this height will be your, so this is how you build that. Okay, so this is the pressure diagram. So let me just draw only the exterior edges. So this is that area of cross section, this is your, okay, so this is your pressure diagram where these are your pressure at the top and pressure at the bottom, and it doesn't vary, the pressure doesn't vary in this diagram. So you have a you have a prism with the face, you have a trapezoidal prism. The face is trapezoid, and it's a prism because you extruded that trapezoid prism. So now the pressure diagram, if you're able to build this pressure diagram, which is easy, I mean let's say this is the height h2 minus h1, this is the width b, and this is your rho g h2, and this is your rho g h1. So the basic from the derivation it comes that the total pressure is nothing but the volume of the prism, trapezoidal prism. So let's see, so this is one important concept. So volume of the prism I can easily find. What is the area of the trapezoid into the width or the extrusion. So area is of a trapezoid, so this is the area, right? This is rho g h1, this is rho g h2, and this is h, which is h2 minus h1. So area will be half of the mean, which is rho g h1 plus rho g h2, half of that mean into the distance h. Width is b, so this is the volume. So rho g h1 plus h2 into h, I can always write h2 minus h1 into b. Okay, so now h2 minus h1 into b is the area of the cross section of this, and rho g h1 plus h2 by 2 into area of the cross section. Now h1 plus h2 by 2 is basically, if you look at this area, that area is nothing but your b here and here. So the centroid of this will be basically your h1 plus h2 by 2. So I can write rho g x bar a. So I get back whatever we have derived, w a x bar. So this is correct. So we can say that the total pressure acting, or the total force that is acting on a vertical plane surface, is nothing but volume of the pressure diagram. Okay, so this we have seen. We have whatever we have derived from the formula is nothing but the volume of the prism. So the total pressure is nothing but, or the total force magnitude is equal to the volume of the pressure diagram. So pressure diagram, the way you have to build is one side, one face is the cross section, and you have to just build a trapezoid with the pressure and then extrude it. So this is your pressure diagram. So volume of the pressure diagram, which is a prism. So this, it will be a prism only for your rectangular cross section. So adopt this procedure for rectangular cross section. And so this is one important fact. The other important fact is about the center of pressure. So center of pressure, from the derivation it turns out that the center of pressure is equal to basically the location of the centroid of the trapezoid face. So trapezoidal face. So the trapezoidal face is this, your rho g h1, your h, and this is rho g h2. So this is trapezoidal face. So find out the centroid of this. Okay, so how will you find out the centroid of this? By breaking it into rectangle and triangle, and from this water surface. So you can basically find out your x bar. So your x bar for this is what is xp. That's what is x bar for that area is. So for the rectangle, how do you get a1 x1 by a2 h2 by a1 plus a2. So a1 is for this rectangle, you can find out the area. X bar for this rectangle will be h by 2. For the triangle it is 2h by 3 from the top. So based on that you can find out location. So this is an important point. So whenever you have a rectangular cross section vertical surface, you need not remember the formulas, just build the pressure diagram. Volume of the pressure diagram, which is volume of the prism, is the total force, and the centroid of the volume. The centroid of the volume is nothing but, because it's a extruded body, the centroid of the prism will be nothing but the centroid of this trapezoidal face. So find out the centroid of this trapezoidal face, that is the center of pressure. So you will get your F as well as your XP bar. So this pressure diagram will be especially useful when you have plane surfaces which are in contact with two fluids, or partly with one fluid and partly with another fluid. So then this concept will be useful. So now let's see for the curved surfaces how to find the hydrostatic forces. Okay, so if I have a curved surfaces, let's say something like this, and this is the free surface, water surface. Okay, so how do I find the curve on this curved surface? Okay, so best thing would be to mark these A, arc AB, and the simplest procedure to do this is project this, drop a vertical projection and drop a horizontal projection, you get something similar to this. Okay, so this is my surface. Okay, remember this is my surface AB. I drop a perpendicular on this vertical line. Okay, and let's call this is C. So if you consider AB, okay, okay, the forces due to water, because the pressure distribution will be all in this way, right? It's normal, the pressure distribution is all normal to the surface. So due to that pressure distribution, you have a vertical force Fp and a horizontal force Fh. Let's say if I happen to resolve this pressure distribution horizontally, I mean, if I consider small element, on that the pressure distribution will be like this, P into dA, and then if I resolve, I'll get some small horizontal force, small vertical force. Sum up all the small horizontal forces, you get FH. Sum up all the small vertical forces, you get FH. So this is the force on this. So we need to basically find FH and FP. What I do is consider the fluid element or fluid element volume. Consider the fluid volume in the arc ABC, or in the volume. I mean, let's not call R. In the volume ABC, consider the fluid. So you have the fluid like this. Okay, A, B, C. Okay, so now on this fluid element, let's put the forces. So you have a top force which you get because of the weight of the water present above, or you know this is like a horizontal surface, right? So you know the pressure there. So because of the pressure, you can find out this force, which is F. Let's call it F1. Okay, so F1 will be basically, you can get from the pressure distribution, rho g h. This height is h. Okay, rho g h into the projection of this, so length BC into width, into the perpendicular width. So you can get F1. F1 is basically on the horizontal, the force on the horizontal projection of the curved surface ABC. Horizontal projection of the surface AB. And from, so here also you have water, right, to the left of AC. So you will get one force that is like a vertical surface. So you get another force F2. So F2 is the force due to the vertical, or for the force on the vertical projection of surface AB. Okay, so surface AB, when you vertical project, so that is nothing but force on AC. So this is force on BC and this is force on AC. So you got F1, F2, the forces due to the fluid outside this volume, and you have the weight of the fluid inside this ABC. And now this FH and FV is nothing but the forces exerted by the concrete or the surface AB on this. So that will be in the reverse direction, right? Because these are exerted by the fluid on the surface AB. Now when you are drawing the free body diagram of the fluid, you need to represent the forces exerted by other bodies. The other bodies is concrete, so FH and FP. So now if you do a force balance, because it's a static fluid mass, so it is F2 minus FH will be 0. So we want FH, basically the force exerted by water is F2. F2 we can easily calculate, it's a force on the vertical surface, so we will get FH directly. Now if you balance the vertical, it is F1 plus W minus Fv is equal to 0. So the vertical force that is acting due to water on the curved surface AB is basically F1 plus W. So F1 is the force, the horizontal force on the, the vertical force on the horizontal projection, that is BC, which is just like your horizontal surface, you can find out, and weight of the fluid present. So in these two ways, we'll do a problem on this. When we consider these two, so we'll do in this way. So always whenever you have a curved surface, project it such that you get a vertical surface, project it such that you get a horizontal surface, and then consider the volume of the fluid inside that sector or inside that volume, and just balance the forces, so you get FH and FP. So we'll solve one problem on this.